Recorded, it's rolling. It is Monday, April 20th. Right, so we've got a bunch of small demos for you guys. And tomorrow's, if I get through everything today that I want to get through, then tomorrow will be a lab day, or at least these are coming up pretty soon, so possibly tomorrow. I might have you guys construct each of these here. But what's the physics principle behind, say, how does a compass or electromagnetic or motor even work? Well, it involves some content that I haven't quite gotten to today. And so we're going to look at capacitors and inductors, also today inductive coupling. And it's all going to lead to, if I pace these out right, I want to play some Paul Hewitt videos today to show how electromagnetism works. Right? And so first, some demos here. I got a couple of cups. I'm going to put some water in one of these cups. Like that. Okay. Now you need an optimal amount of water, not too much, not too little. So hopefully I got that. We're going to find out. I got a stack of bar magnets. Now you have to know where the poles are on these magnets. So they're on the faces. So this right here that I'm pointing to, this is either the north or the south, and on the opposite end is, well, either the south or the north. Guys, can magnets have a single pole, or do they always have a north and a south?
They always have.
Yeah, there's always a north and a south. There's no such thing as a magnet that's only north, or at least conventionally. So, right? Well, how about this? Okay, break this apart like this. Now they're individual magnets, aren't they? Okay, so this one all have the north and south, and giant north south here. But if I stick them together, now we're back to one giant magnet. Okay, if I put this in the dry cup, okay, and then I put the dry cup inside the wet cup, so it's going to float around. Let's see what happens here. Oh yeah, okay, got this about right. Should align to Earth's north-south field. Ooh, I think north is that way. I'm pointing towards north. And if I rotate this, it should rotate back. Let's see if it does. This is giving me trouble today. This always works, but not now for some reason. Okay, I don't know why this is being finicky. Well, okay. Sorry about the terrible example. I have no idea why this is not working right now, but usually this will actually reorient itself. Okay, there it goes a little bit. Okay, so now it just reoriented. Just saw it move a little bit. Okay, however, these are not exactly straight up. Okay, so there's how you can create a compass. That's all a compass is. You put a magnet, let it float, and it wants to align to Earth's magnetic field. So possibly more on that later. What are some of these other things? Electromagnet. Right, so I got some thinking. Notice this says electromagnet. So I'm going to get rid of the bar magnets. Notice there's no bar magnets on the screen right now. But instead, I'm going to take this coil of wires. I'm going to coil it around this bolt. Okay, so around it goes. Okay. Now notice this wire is insulated except for the ends are stripped. You guys get the ends are stripped. All right, and there's some copper wire here. Copper is like the best element for these classroom demos. Right? We get like aluminum, it just doesn't work as well. Okay. And so wrap this around this bolt. And then I'm going to bring in this battery. Do you see any permanent magnets on screen? No, there's no permanent magnets. But once I attach the ends of the battery, the leads of the battery, let's see, I should be able to pick up these paper clips. Look at that. I can pick up a paper clip. Now, what do you think would happen if I disconnect the battery? Do you think it's going to pick up anymore? Okay, so disconnect the battery and, it doesn't do anything. So you can create a magnet with no permanent magnet, right? All you need is some kind of electricity source, or get electric current, get it to flow around in a circle like that. So there's your electromagnet. Now the motor, okay, here's one I got to work earlier, although this is sometimes kind of finicky, so we're gonna see. But I got a stack of bar magnets. Okay, so got one of the poles straight up. I'm gonna take these paper clips and extend the leads of the battery. So now I can extend the cathode and the anode. Like that. Okay, I got a wire that's insulated, coiled around, and then the ends are stripped. Now, guys, the fact that the ends are stripped is allowed to make contact with this metal and then make a complete circuit. Okay? Now, when I put this coil in this magnetic field, okay, gotta make sure the metal's touching the metal. Right, it will. Oh, yes. It's spinning. You guys see it spinning right there? Was. Okay. Now, guys, how long did that spin for? Exactly, until the battery runs out, because that's the source of energy, isn't it? Energy's coming from the battery. Okay. Ooh, it feels hot. I feel it feels hot. Right? Because it's sort of a short circuit, wasn't it? Right? There's hardly any resistance in that circuit you just saw. Okay. Hey, how do you think a ceiling fan works? How do you think anything with a motor in it works? I mean, that was a motor right there, wasn't it? That was a motor. Guys, if you have an appliance, you turn it on, a vacuum cleaner, blender, whatever, ceiling fan. That's what we're doing is we're taking an electric current, we're putting it past the magnetic field, and somehow that's inducing like a physical force. Ooh. Hey, I wonder if we could go backwards on that. Do you think you could take a force, put it next to, let's say if I force this, could I generate an electric current that way? Huh. Hold on to all those ideas. Actually, that is the next example I got right up right here. Oh, where did I? Here it is. Yeah. Faraday flashlight. Okay. I used to have a bicycle light that was like this too. Like, there's no conventional battery inside this flashlight. What there is a big old magnet and the coil wires. If I shake that back and forth, it's kind of like the motor process you saw, but exactly backwards. Okay. And then you can turn on the light. Turn on the light. Okay. Okay. So now, where it does store the energy is in probably a capacitor here, and I think is what it is. There's a capacitor. So more on that later. Got that? And then here's another version of the same idea. Right. If that bulb just turn on. Right. No, this one doesn't really have a storage method, but they can turn on in an instant. Okay, so now we're doing something else but interesting with electricity that also involves magnets. So there's some magnets there. I got back magnets here. Right. We got generators. We got motors going on. Right, and I wanted to fill in a few details also from last week I didn't get to. Right, so shuffle back and forth a little bit here. Can you see this breadboard? Now, I had you guys wiring up some Christmas lights and using 9 volts, but if you want to do a little more upscale version of this is a common thing to use is this breadboard. And you can put in appliances on the side with all the holes in it. The name comes from way back in the day. They actually used to use physical breadboards and like drill a bunch of holes and stuff. But after a while, I say, hey, let's come up with like some thing that everybody knows how this works, like some convention. And if you turn it around, and sometimes there's a sticker on the back, and you take off the sticker, you see these metal strips, right? So that can tell you how these connect together. So like I would never put an appliance in like this hole and this hole because no way would it ever turn on. It would always be shorted out. But if you bridge this gap in the middle, now you can start to create a circuit from that. And you guys see these long strips of metal on the sides? Now these run all along the sides. Sometimes they're called buses and sometimes they're called rails. Right, so look at that. Okay, so now you can create giant circuits too. Right, so back over here, I want to show you guys what this looks like. Okay, so here's a breadboard with some things in it. But look at all these little blue things. They got little colored bands on. You guys see the colored bands? More on that later. These are resistors. I got a little LED here. And okay, here's a simpler looking one. Right, so if I take the cell phone charger, does anybody happen to remember from last week how many volts is the cell phone charger? It's like 5 volts. So I'm gonna plug this in. No, guys, do I want to go jamming any paperclip into this alternating current right here? 240 volts, or is that 120 volts? No. Right. But if I plug this in, now this is gonna be an adapter. It's gonna convert 120 volts alternating down to just 5 volts DC. Okay. Now this is safe. Now I can mess with these. Okay. So where my paper clips go? Okay. I'm gonna use these as leads. Okay, and see if I can get these LEDs to turn on. Now I know if I put in a lead right here, bam, I'm gonna connect to that bus and connect to this LED here, which bridges over to this LED, which bridges over to this resistor. Ideally, I want some kind of resistance here. Okay, and I'll use this as another lead right here, connected to this rail on this side, this way. Okay. And then let's see. Now LEDs only work in one direction, so 50-50. See if this lights it up. Okay, so not that way, so maybe I got my leads backward. Let me try the other way. Oh, there they are. Okay. You guys see, I don't know how well it showed up on camera. Okay, where'd it go? Okay, but this one's green and this one's red. Oh yeah, they're showing up. You guys see a green and a red LED? Okay. Okay, so there's a little bit on a breadboard right there. Breadboard. Okay. All right. All right, how about inside a battery? Right, so some way to store energy chemically. Right? Now there are different kinds of batteries. Battery technologies, still improving, come a long way in recent years. But this is a conventional battery. You could probably buy 30 years ago even. Right? So you need some kind of cathode, some kind of anode, and some kind of electrode in the middle. Right? Okay, so there's some chemistry here. Here's a common design. We've got manganese dioxide, we got zinc, and then we got this electrolyte, potassium hydroxide. Okay?
And then if you can make some kind of connection, create a full circuit. So chemistry going on inside there. Okay, here's something I never got to last week is capacitor. Now that Faraday flashlight, I was shaking it up and then I could turn it on. Well, the energy was being stored, but it wasn't in a chemical battery. It's in these parallel plates. So you just have two parallel plates, right? And then you can store energy that way. Now, if you have one of these in your circuit, here's what it causes to do. It causes the voltage to lag. So if you hit the on switch, like close the circuit, hit the on switch, the voltage slowly builds up. And then you hit the off switch, the voltage will still be there and it will slowly dissipate. So it doesn't turn on and off right away. Okay? Now, another device you can have is this inductor. Hey, you guys just saw one of these. Didn't I just take a wire and coil it around that bolt? Right, so that's the basic inductor. So coil wires like that, right, inductor. If you have one of these in your circuit, one thing it'll do is it'll cause the current to lag. So hit the on switch or the off switch, the current will slowly build up and slowly dissipate. So it won't turn on or off immediately. Okay. You can do other things with inductors. Interesting too. Right hand rule for electricity. You guys remember for torque? You guys saw a right hand rule? It's like R cross F results in a torque. Okay, so similar idea here. If you have some electric current, that's what I is measured in amps. And so, ooh, what do you guys think B stands for? I haven't told you guys yet. Um, what other device I have up here actually starts with an M? Magnet. Aha. So B is magnetic field. You can quantify that in Tesla, which breaks down to different SI units. Right? Physical force, F, which you can measure in newtons. Okay. So this is like the motor that I just put together with the battery and the magnets. You get electric current and a magnetic field, you can create a physical force. That's a motor. Or you can reverse all this. So you can force a wire past a magnetic field, and that'll generate an electric current. Okay, that's how electricity is generated. That's how the lights are on right now. That's how the air conditioning. That's how this projection's on. Right? Because there's some power plant miles away that's doing that. Right? So there's a flip side of that. But that would be Faraday's law. Right? So Paul Hewitt has a really good demo that shows that creating a voltage just by running a wire in and out of a magnet. So you'll see that later. Oh, here's your lab tomorrow. So got this mini lab trio. Didn't I just put all these together for you guys? I don't know why the compass was working or was not working. It always does, right? But yeah, until you guys get these to work tomorrow, there's all the ingredients for those. Okay. And okay, got solution. Okay, so here's how you create those. Boom, 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 just like that. Okay. And then a generator and a motor could internally look nearly identical. They're just doing opposite processes. So what a generator will do is it'll take like a physical force, say if you're turning this physical into some kind of mechanical force, it'll take that energy from that motion and it will convert it into electrical energy, which then you can put onto the grid. And then on the opposite end of the grid, you can have this motor where you run that electrical current, which contains energy, past magnetic field. It will generate a physical force. And that's where you saw that motor spinning. You see that? So generator and motor are really same device doing exactly opposite processes. Yeah. Oh, inductive coupling. So if you look at the power lines outside, see power line, there might be like thousands or tens of thousands of volts, and yet linked to this building, it jumps down to just maybe 100 or 200 some volts. Okay, so how do you get voltage and current to change? Right? Oh, and the reason for that is it's more efficient to have high voltage, low current, and then reverse the process when you're actually uh, transmitting that to a single building. Okay? So you insert a transformer, which plays off inductive coupling. I do have a video demo on this too in some of these, right? But slides first. So the voltage is proportional to the number of coils. That's that bottom right formula. And the electric current would also change. The inverse proportion applies. So that's this multiple on the left side. Okay. But the overall power is conserved. You guys remember power is current times voltage, P equals IV? You guys remember that? So that also shows conservation of energy. So if one of these formulas is true, the other has to be true by conservation of energy. Okay. Three-phase alternating current. So yeah, you'll see like different power lines. They actually put it in three phases so that it doesn't like go to zero and blah, blah. So they actually have like three overlapping voltages going on, right? For alternating current, right, where it alternates. Okay, and then okay, this is way beyond the scope of high school, but if you go into electrical engineering, got some crazy math here for Maxwell's equations, which actually eventually leads to a theory of relativity. Interestingly enough, right? So, all right, that's all the slides I got there. All right, let me find. Um, All right. Did I show this one to you guys when it loads? Direct current versus alternating current. You guys see that? Okay. Right. And then for anything linked to a battery, it's direct, but anything to a wall outlet or off power grid is that alternating motion, right? You guys see that sloshing back and forth? There would be some frequency associated with that. Uh, did I tell you, or do you guys know what is the frequency for North America, the frequency standard? Yeah, 60 hertz. Yeah, 60 hertz. Yeah, if you go over to Europe, it's like 50 hertz or something. But you have to have a standard so you can connect appliances to it. All right, let's look at
Hi, folks. Here's a neat.
oops, capacitor. Now, Ben Franklin in the day worked with these Leyden jars, which were a basic type of capacitor. Watch this little spark here. Spark, right? No, his two parallel plates are actually cylinder shaped in this case, and it's separated by like some little plexiglass or something. So he's going to charge it up, and then it gets a little spark out of it. So it's sort of like a battery, but it's not chemical energy. It's stored in these electric fields, right? And then he goes on and talks more about it and says, oh, it feels like a prickly feeling on that plexiglass. Says, hey, I think the electric field is actually stored on that plexiglass, not actually on the metal. So that's kind of interesting. This is a more conventional type example. So you could put this in a circuit, this capacitor, and this is an ultra capacitor, so it has a huge amount of capacitance. Look at those sparks flying right there. Goes through, does some math on these things. Okay. You can measure capacitance in farads, so talks about that. All right. Wires these things up. All right. Just burns lots of things. All right. While he's talking about the math behind this. We're not going to get too deep in that in this class, other than I want you guys to be aware that exists. All right. All right, let's switch over to inductors. Oh, look at that. It's just a coil of wires. You guys see a coil of wires right there? All right, let's see what you can do with inductors. So if you have an inductor, didn't I tell you the current would lag? So if you hit the on switch and close the circuit, the current flows, but it takes a while to build up, and then you hit the off switch, and look, it takes a while for the current to dissipate. So the current will still continue to flow, even though the circuit is open. Not forever, right? But it takes a while for it to dissipate. And then you can get inductive coupling out of this, which he does near the end of this video. They find it. Right. So, oh, look at that. See, it has one inductor next to another inductor. Notice those wires are definitely not touching. There's definitely a gap between these two. Hey, how do you do wireless charging? Right, let's say, I know some phones will wirelessly charge, just like put them on a pad and they'll charge. You don't have to plug anything in. Right? Oh, well, it's probably because they got these little inductors up. Oh, look, and there's the reading. So the closer they get, the stronger the reading, right? And then the farther away they are, right? It's not as strong. Right. Here's another example of this inductive coupling. So you got some battery source in the back. You guys see this voltage source, this big black box. Okay. And then a big old ring here. And on the right side is another copper looking ring. And then this light bulb. Okay, so you just turned on the battery. Now guys, watch when he plugs that bulb into this copper ring. Watch what happens to the bulb. Let's see. Oh, it turns on, even though it's not actually connected to the power source. The power source is over here. Okay? This is a giant inductor. Watch when he gets it closer. Ooh, did that just get brighter when he got it closer? Sure did. Sure did. Right? What if he turns this different ways? Watch real closely. He's gonna move this around, turn it. Ooh, did you guys see it just blink off? Blinked off? All right. Let's see. Turns it 90 degrees, turns off. Okay, because the energy is trying to transmit, but if it's not lined up correctly, it's like orthogonal, then nothing transmits. Yeah. Okay, so got some inductive coupling going on there. All right, I got induction heater. Oh, we need sound for this one. Induction heater. Ooh, so I'll heat up. Now I have a demo up here because it's actually a version of this. Let me see if I can dig this up while he's showing you guys. Oh, yeah. Ooh, actually, I got two. I forgot about it. Okay. So, did you guys see at the very beginning, he touched that magnet to that copper casing, and there was no magnetic attraction at all. Did you guys notice that? Here, let me back up, for just in case you missed it. So, look, tap, tap. There's no attraction at all. Okay. If you guys try to pick up a penny with the magnet, you can't do that. Most American coins, you can't. No, I think no American can you pick up with a magnet. But he drops it through, and there's some kind of interaction going on because it's definitely not in pure free fall. There's some kind of resistive force. You guys see that? So the principle here is called Lenz's law. So that when you have a magnet that's moving next to a closed loop, then that will induce a voltage and therefore a current, which induces its own. It's called eddy currents. Right? Will induce its own magnetic field, which always resists the magnetic field of the original. Okay? And actually, this is part of what you need for conservation of energy to make power plants work and electricity generation. Right? Because if that did not happen, then you'd be getting energy for free.
right? But the fact that there's some kind of resistance to that motion. And so here I have, my version of this here. I got these magnets, got this copper, but there's no attraction at all. No attraction. Doesn't. Right? But if I put this in here, let it fall, it falls down very, very, very slowly. Okay? And it's not because of friction. It's because it's a closed loop. Okay? Now this is supposed to show the same thing. Doesn't show it like as well, but there's some magnets inside here. Got this, and it's like, okay. It's supposed to not be curve ball, but that's what it's supposed to show. All right, what else we got? All right, let's look at simple motor here. All right. No, tomorrow I'm gonna have you guys build a motor, but this exact design is really hard because you have to balance this exactly correctly. Some students in the past have tried that, but that's really, really hard to put together. Also, I don't have, I think, circular magnets that look like that. But look at that. Hey, guys, what about this? Notice you just set it on top and just start spinning. How long will that spin for again?
Battery runs out.
Yeah, until the battery runs out, because that's the source of the energy. Because what if you took this magnet and you flip the magnet upside, sorry, the battery I meant. If he takes the battery and he flips the battery upside down, what do you think would happen to the spin? Huh? You think it would switch from clockwise to counterclockwise? Go back the other way? Yeah, because the links back to that right hand rule page I was showing you guys earlier. There's a reason it's spinning clockwise. It has to do with which way is the current flowing, which way hey, what about the magnets? What if you flip the magnets upside down? Do you think that would also reverse the spin? Yeah. If you flip both the magnets and the battery, I bet it would go back to how it's spinning already. Flip up. Okay. Let's see what I got for magnetism here. Let's look at magnetic field. All right. So, great. Got some magnets, got some paper clips. All right. What if I throw a paper on top and then throw some iron filings? And then you can see the magnetic field. Right? It's like a 2D cross section of the magnetic field. You see those lines right there? Right. One to pull together. Right. So here's a animation representation of that. Okay. So there's a convention. We always draw the lines going from north to south to provide some kind of direction. That can help you with the right-hand rule and figure out like which way is the motor going to spin and all that. Right. And notice so we got some lines out here. Right, which are a bit weaker, right, but you want to draw north and south. You have a giant bar magnet. What if see? Okay, the lines go north to south. You guys see that? The convention. What if I break the magnet? Right. You guys see they're tracking here north to south. And if I put them together, they right, create one giant magnet. And there's one I missed in the middle. Where is it? Where? There you go. Guys, what do north and north do? Attract or repel?
Oh,
Repel. Okay, so the same pole is going to repel. And notice that the field lines don't even cross when they do that. Okay? So the field lines want to attract north to south. So if you put north and north, they don't even cross. Right. Now, there's another concept called flux. So if you take this magnetic field, you guys see all these blue lines labeled B for magnetic field, right? And you rub off some area. Doesn't that coil of wires I was showing you guys earlier have like some cross-sectional area? Yeah. Then this is called flux. So here's Greek letter phi to represent flux. So if you rotate the coil like that, it doesn't change it because the area doesn't change. Okay. But what if you double the area? Would that double the flux? Because here's the formula. Flux is magnetic field times area. Right. But something about this angle is what if you rotate that area 90 degrees? Now none of the field can get through the area, so the flux is just turned off, just turned to zero. What if you keep going, turn it negative? I can get a negative flux. Okay. Finally, what if I have some weird area? Show of hands. Does anybody in calculus? Anybody take a calculus? Right. So one process we'll see in calculus, especially get to the integration side, is like if you have some weird shape, you guys say that weird shape, how would you figure out the flux of that? What it ends up being is just very simply, if you were looking at it head on from a long distance away, you say, oh, that looks kind of like the original rectangle anyway, so I'll treat it that way. It ends up being identical, right? But the calculus thought process is, what if I split this into like 100 tiny squares, right? And then each square is approximately flat square, right? And then I could add up all the fluxes from that, right? So there could be some flux from this individual square and so on. Okay. That, right, let's look at about Earth. Right, you guys ever seen, has anybody ever seen the Northern Lights? Anybody, who's ever seen the Northern Lights? Anybody seen these? Like been up? No, nobody? Neither have I. But if you go up to like way north, you might see, right? All right, but what's going on here is sun's cosmic rays are leaking in Earth's magnetic field. So from the side,
it could look like this animation. I got, see, here's Earth, left is day, right is night, right? And here come this cosmic rays from the left, the sun's way to the left, right? They're seeping in. It looks like the north and south magnetic poles. Right now, why does Earth have a magnetic field? Right, so uh, probably because of convection currents going on inside the mantle. Right, so way back billions of years ago, most of the heavy elements tended to sink down inside, and most of the lighter stuff tended to stay on top. Right? Here at the spinning, right? You guys remember that Coriolis effect from last semester and so on, right? So probably a lot of these effects are going on, right? Causing Earth to have a magnetic field. Now, if you look at the surface of Mars actually has water erosion all over it. But there's almost zero water on Mars. Right? So what happened? And it's a very thin atmosphere. It's like less than 1% the thickness of Earth. Right? So what happened? Probably what happened was, see, Mars is a smaller planet than Earth. So Mars probably had at one time these convection currents and magnetic field and the whole thing, which gives us a magnetosphere. So Earth has, right, which protects us from a lot of the cosmic rays. But because Mars is a smaller planet, it cooled off faster. Think like geothermal, basically. Okay? And so this whole process stopped. So Mars lost its magnetic field, and then because of that, cosmic rays were able to bombard its atmosphere, and it lost its atmosphere. All right, let's look at. Here, just got a couple more for you guys before Paul Hewitt. There's different kinds of magnetism. Most people think ferromagnetism when you think magnetism. So I can pick up a steel paper clip with a magnet. Okay? But what's this going on here? So water. I meant to ask you guys, what is that frog mostly made out of? Yeah, water. Right? Actually, that's true for us too, isn't it? Aren't we mostly made out of water? Right? So it turns out that water is actually diamagnetic. It weakly repels away from a magnetic field. Right? Actually, if you have a bowl of water and you put a magnet right near the surface, it will bend down a little bit. Right? So if you have throw like a little frosted flake in it, it can like fall around because the water actually dips a little bit. Right? And in this case, you can actually levitate the entire frog, or same thing with a strawberry for you guys. Yeah, the whole strawberry is being levitated because it's mostly made out of water instead of giant magnetic field. So it's sitting there. Okay, hang on, let me pause this video, grab this phone call. All right, we're back recording, and guys, the rest of the class today, I just got some Paul Hewitts for you guys. Right, and then tomorrow will be a lab day. I'll help you guys construct all those things that I created at the beginning of the class.
Source of that magnetism was betrayed years ago, more than 150 years ago, by a fellow by the name of Hans Christian Ørsted, who was a professor type teaching, I believe he was in a high school classroom. And he was showing the students that there's no relationship between magnetism and electricity. The physics books at that time had electricity as one subject and magnetism as another. And Ørsted was showing there's no relationship between the two. And one of the things he would do is he would line up the piece of wire like this and put it over a magnet, pass a current through it, and you really don't see anything happening. There's no interaction. But after class, a student came up and held the wire in this direction, and when a current passed through it, okay, watch this, when a current is passed over the wire like this, boom, you see that interaction? It turns out there is an interaction between a current carrying wire and a magnet. And it turns out, to make a long story short, the source of all magnetism is moving electric charges. And when the charges move through the wire, they spout the wire a magnetic field. And that magnetic field is in concentric loops around the wire. If I pass this wire through a hole in a piece of paper, and I put a whole lot of little compasses around the wire, and no current goes through, all those compasses would point north. But you know what would happen if I put a current through that wire? All the compasses will line up with the field. And it turns out that field takes the shape of concentric circles about the wire. The further away you get, the weaker they get, but the direction is all that way. So surrounding every current carrying wire is a magnetic field that takes the direction of the concentric circles. I want to show you something that's even more interesting than what we've seen. Let's take this magnet. I'm going to put the wire in the magnetic field of this magnet, and I'm going to touch this momentarily so I get a pulse of current. And when I do that, when a current goes through this, would this wire, in a sense, be a magnet? How about when no current goes through it? It's copper wire. Copper is not ferromagnetic. Copper, you've all tried when you were a kid to pick up a penny with a magnet. It doesn't work, does it? Because the penny's copper, okay? So the only way you're going to get magnetism with copper is to have boom, electrons flowing through it. Electrons flowing through anything would set up a magnetic field around that anything, yeah? Let's see what happens with the magnetic field of the wire and the magnetic field of the magnet. Let's see if there's any interaction. What do you suppose? Watch this, gang. You see that jump down? See that jump down? Let me turn the magnet around. Jumps up. Did you see that? I'm going to do it one more time. Watch. Wow, jumped up. So one way it jumps up, and the other way, put it this way, it jumps down. I wonder if that jumping motion could be harnessed. How many people say, well, no, there's probably no practical application of that. Wires will move in magnets. Big deal, right? Is it a big deal? It's a very, very big deal. Because guess what this underlies, gang? Electric what? Begin with M, end with odors. Try it. Motors. Any electric motors be working on such principle, okay? And dig this. Whenever you see any electric motor, realize, you know, sometimes we see things and we're so overwhelmed with the complexities, we don't know what the nitty-gritty is. Realize the nitty-gritty of an electric motor is simply a current-carrying wire boom, being deflected in a magnetic field. Period. That's it. This was done by a couple of physicists about the same time in history. One was Michael Faraday, a Scottish guy in England, and the other was Joseph Henry, an American type in Vermont in the 13 colonies. And they both at the same time found the same effect. And here's what they discovered. They had meters similar to this at that time, but they didn't know how to get electricity. Well, they got electricity from batteries. A fellow by the name of Volta, Alexander Volta, Italian type, made batteries, and that was kind of nice. Everyone's excited about electricity. And then Michael Faraday and Joseph Henry discovered the following. No batteries over there, gang. No batteries, no tricks. Magnet, wire, meter. Watch this. You see anything? Faraday didn't see anything either. Okay. Okay. And but watch this. Henry didn't say anything either, but watch this. Did you see something? Again. My goodness. My goodness. There's no battery nearby, and guess what we are generating? Begin with EC. Electric current. I am generating electric current. And Faraday and Henry found out that. No batteries, no cells, none of lightning, none of that. Just the motion of a wire in a magnetic field. So Faraday goes to bed and he's really excited about that. And while he's in bed that night, I'm making this up now. While he's in bed that night, he's kind of thinking, gee, I wonder what would happen if I did it with 2 wires. So he gets up in the middle of the night, takes his candle, goes downstairs, had to do a candle. Little did he know that he was going to get rid of candles, and the candle industry was furious later on, okay? But what he did is he went down and he took 2 wires, and guess what happens with 2 wires, gang? Boop! Twice as much current. Goes back to bed. Then he thinks, I wonder, 3 wires. Shall we try it? Didn't sleep.
You guys see that? Every time he puts another loop in it, you guys see it jumps up another like another volt here. Right. Okay, so like 3 times the loops is like 3 times the voltage and so on. Right. So that's all going to go into what's called Faraday's law. Now, guys, do you get something for nothing from that? If you do like 1,000,000 wires, do you just get like 1,000,000 times the energy, just like generating energy from nothing? Is that how thermo works? Or wait a minute, what do you think the catch is? You guys remember that Lenz's law you saw earlier with the magnet going through the copper pipe? It went through more slowly. Oh, so every time he puts another loop in it, Do you think it actually there's a resistive force and actually more difficult to run it past the magnet? Yeah, that's where the energy's coming from. So energy is still neither created nor destroyed. You're just transferring energy from a mechanical form onto an electrical form.
So the night gang. I wonder, a million wires. What do you think? A million times as much. Okay? This is a remarkable discovery that one can, it turns out, induce voltage by simply moving a wire in and out of a magnetic field. And so Faraday's discovery is couched a little differently. Today it's called Faraday's law. And what it says is this, a little more complex. Change the magnetic field in a closed conducting loop of wire, doesn't even have to be conducting. Just change the magnetic field intensity in a closed loop, and you will induce a voltage in that loop. Now, this loop happens to be a copper wire, so the voltage in that produces a current. So look at this. You get a current. Change the magnetic field in two loops of that closed copper wire, two loops of that circuit, and guess what you get, gang? Twice as much voltage. Three loops, So that's the rule. All you got to do is change the magnetic field intensity and you will induce a voltage, which will produce a current if you're talking about a conductor. Ain't that neat? That is really, really nice. Now we can produce electricity. You know how all of Europe started converting to electricity? They started having lamps and all that stuff, and they had all these kids up in the hills going like this. Okay. And these kids are all doing this thing, okay? And one day they say, hey, we're getting tired doing this. See that waterfall coming down? Why don't we put this wire on a great big piece of wood and have it rotate, huh? By the waterfall, put a little paddle wheel and we'll go home and get all electricity. And that's, of course, the start of the Industrial Revolution. I'm making that part up, but you get the idea. All you got to do is rotate the loops in a magnetic field or just plop in and out of the magnetic field, and there's your electricity. Faraday's law. Hey, you know what? You know what is a neat application of electromagnetic induction? It's just been the last few years, and that's the smart lights. When you're traveling down the road and you're coming to the traffic light and the lights change for you. You drive over something and that something changes the lights. They used to put like a piece of rubber tubing out there with compressed air and it would boom, make a little pulse of air and that changed the light, but then the rubber would wear out. What they do now is they bury in the road a coil of wire.
Right. Here, let me draw this up. We got guys. Next time, oh, sorry, my screen's being all glitchy. Okay, guys, next time you're driving around Vieira, look really close in the road intersection. Let's say you're like driving up, right? You might see some shape that looks like this in the road or something like this, right? So you drive up to the light, right? When your car rolls over that, it'll change the voltage, and then that'll send a signal to the light, and then it'll know your car's there. Right, so that's what he's talking about here.
Okay. Wire buried in the road. Now, through that coil of wire is a magnetic field of the Earth. And part of that field is in that Earth, all right? Now, if you could change the magnetic field intensity of the Earth through that big coil of wire, what would you induce in that coil? Begin with a V, of voltage, isn't that right? So when your metal car drives, when your iron car, a wooden car won't work. When your iron car goes over that coil of wire, does it not alter a little bit the magnetic field intensity in that loop? Answer begin with a Y. And when it does that, it makes a little tiny electric current, which activates the switch of changes the lights. Isn't that neat? And that's what happened in this case. In 1820, a rather dull dame called Ørsted was teaching his students that an electric current going down a wire shouldn't have any effect whatsoever on a compass needle. When, to his utter chagrin, it did. Well, no fool he. Ørsted immediately made it known that if an electric current going down a wire caused a compass needle to swing, it had to be generating a magnetic field and moving the needle. Poor old Ørsted. I mean, who's ever heard of him? Michelangelo, yes. Ørsted. And yet, the fact that an electric current generates a magnetic field is fundamental to the way the world is run today. I mean, take just one thing that happened because of Ørsted.
If you wind a live wire round and round a bit of iron, the magnetic field generated by the current causes the iron to become a magnet, an electromagnet. Now, somebody did that in England in 1825. In 1857, a German took a tuning fork and put it next to an electromagnet, turned it on and off, turned the magnetic field on and off, and caused the tuning fork to vibrate. And then in 1870, a Frenchman living in America took a diaphragm, put a bristle on the end of it, and then yelled into the diaphragm to make it vibrate. And the bristle jiggled up and down and made a pattern on smoked glass. And the pattern was always the same for the same word. Now, I say all this because the brilliant invention that came out of it, and it was a brilliant invention, was really no more than putting all those bits and pieces together. Like this. You yell into that cone. That causes a metal diaphragm here to vibrate. Now, that metal diaphragm is within this magnetic field, and as it vibrates, it kind of drains it, causing the current in the live wire to fluctuate. This fluctuating current fluctuates along a wire until it reaches an identical setup, where because it's a fluctuating current, it makes a fluctuating magnetic field. And that causes another metal diaphragm to vibrate in exactly the same pattern as the first one. And when it does that, it makes a noise in that cone. So what you yell in here comes out there. Now that basic idea occurred to two men at the same time. Only one of them, a Scotsman living in Boston in 1875, teaching deaf mutes, got to the patent office 2 hours ahead of the other fella. And that 2-hour difference is why we say that the telephone was invented by Alexander Graham Bell.